Area between two curves. Before we get into this, let me remind you what we learned in the past. The area under a curve like f of x from a to b can be represented by the definite integral from a to b of f of x with respect to x. And if I had a separate function, g of x, and I wanted to represent the area under this curve from a to b, then that would be the integral from a to b of g of x dx. Now, what if I wanted the area between these two curves, this area here highlighted in yellow from a to b? Well, if you said that you're going to subtract your integrals, you would be correct. So you're going to find the area underneath that red curve, the area under f, and you're going to subtract the area underneath the green curve, or the area under g, and that's going to give you the area between the two curves. Well, you may recall from our properties of definite integrals that you could call this like it's written, or you could put it together like so. So here on this slide, we're just talking about, this is the formal definition for finding the area between two curves. If f is greater than g, now that's important. F would be on top of g, or the upper function we call it, and then the g function would be the lower function over the interval from a to b, then the area between the two curves in that interval is that. So you need to write that down. A couple of things to note, that every time you find the area between two curves, it's always going to be positive. Even if, like in this diagram down here, you are looking at the entire area is underneath the x-axis. And the reason that that's positive, if you think about it, is that the area between the red curve and the x-axis, that's going to be negative. And then the area between the blue curve and the x-axis is going to be more negative. It's going to be a larger negative value, and you're still going to do the upper minus the lower. So when you do the area between the red curve and the x-axis, which is, say, I don't know, -1, and then the area between the blue curve and the x-axis is a larger negative number, then you're looking at a smaller negative number minus a larger negative number, which is always going to try to be positive. Hopefully that made sense. So that means that in your calculations, if you get 0 or if you get a negative value, then you can be assured that you've made some mistake and you need to check your work. Let's take a look at an example. Okay, before I go into the integral, I need to figure out which function is the upper function and which function is the lower function. So I know that let me draw a little graph, sketch of the graph here, like so. And, oh, didn't mean to change the color there. And I know that this function, y equals x squared plus 2, that's just a parabola where the vertex is up at +2 and it opens up. So maybe something like so. And then this function, y equals -x, that's going to be the line whose y-intercept is at 0 and whose slope is -1. So maybe a little something like that. Not perfectly drawn. It's kind of hard to draw on a computer. And we're also looking at x equals 0, so that's just going to be your y-axis, and x equals 1, which would be somewhere over here. So we're looking at the bounding this area, this region in here. And we want to find that definite integral. So we're going to go from 0 to 1. The upper function is x squared plus 2, and we're going to subtract the lower function, which is just -x. dx. And if you want, you could put extra square brackets right there. So let's go through and integrate this. So first I'm going to distribute that negative. So I'm going to have the integral from 0 to 1 of x squared plus 2 plus x dx. And then we can apply the power rule. If you want to reorder that, you can. Actually, I'm going to go ahead and do that. I'm going to be crazy. Let's call that the integral from 0 to 1 of x squared plus x plus 2. That's not really necessary, but I like it. So now we are going to find the antiderivative. So it's going to be x cubed over 3 plus x squared over 2 plus 2x that we will evaluate from 0 to 1. So you will recall that we're going to do, we're going to plug in the upper boundary and then the lower boundary. So that'll be 1 cubed over 3 plus 1 squared over 2 plus 2 times 1 minus, put some giant parentheses there, 0 cubed over 3 plus 0 squared over 2. Hopefully you're quickly seeing that that's just all going to work out to be 0. Close parenthesis. So I'm not going to show that calculation, but I will tell you that that works out to be 17 over 6. So that is the, whoa, picked an eraser there. Let's go backwards. I thought I picked the highlighter. Here we go. So that would be the area that's represented between the green curve, that parabola, and that line there. Now keep in mind what's really happening is you're finding a bunch of, it's all back to rectangles, right, in Riemann sum. So you're just looking at an infinite number of rectangles like so. We call them vertical rectangles, if you will. The other thing I wanted to point out is, G, whoops, didn't mean to do that. all of this business of finding the antiderivative and plugging in the numbers and then subtracting with the fractions, it's really getting to be quite tedious at this point. There's got to be an easier way. You know what? There is. Let's go to your TI-84 calculator. All right, I'm going to show you how you can do a definite integral in the TI-84 calculator. First thing I'm going to do is I'm going to go into y equals, and I'm going to type those two functions that we just graphed. So x squared plus 2, and put that in y1, and in y2, negative x. And we can look at the graph. I usually do, when I'm hanging out by myself doing these area between curve problems, I usually will graph them in my calculator just to confirm which function is the upper function. So you can confirm that the parabola is the upper function. Now I'm going to go back to my home screen. And this is where the magic happens. Press Math and go down to option number 9. And one more. Whoops, there it is. It says FN int, which means function integrate. And you press enter. Oh my God, are you dying? Are you mad at me? All this time you could have done this in your calculator and I never showed you until this moment. Well, that's just how I play the game. Let's just move on from this and learn the technique. So what I'm going to do is my lower boundary is 0. You can arrow to the right, or you can probably arrow up to get to my upper boundary, which was 1. And then in here, my first function, my upper function, I have it typed in y1. So I'm going to go and grab y1. So I press vars, over to yvars, into function y1. Minus my lower function, which I have typed in y2, vars, yvars, function y2, and then here you have to put with respect to which variable. It's going to be x. We press enter. There it is. If I press math, enter, enter, it turns into a fraction for me, 17/6. Do you hate me a little bit? I don't blame you. Now, you don't have to do the y1 minus y2. You can certainly just type the functions. If you just go math 9, 0 to 1, and then do, you can do parentheses, x squared plus 2, close, minus, open, negative x, close, dx, enter, math, enter, enter. So you could do it that way as well. But again, I prefer to type them into y equals so that I can see the graphs, and then I just pull them up when I'm doing my definite integral. All right, here's the second example. Pause the video and try it by yourself. All right, so before I get into the definite integral, I need to graph the functions to figure out which one is my upper function. I also need to figure out what their boundary is. I went to my calculator again. This time I chose the color version. And we can see that the line, the 2x plus 1, is my upper function, and then the parabola, the x squared plus 1, is my lower function. And the area that's bounded by these graphs would be this like little sliver of a space right here. So we need to figure out their points of intersection. So there's a few ways that you could do it. This one happens to be very nice. If you went into the table, you can see that when x is 0, they're both equal to 1. So that's one point of intersection from 0 to 0, 1. And then you can see that when x is 2, they're both equal to 5. But that only works really if your graphs intersect at integers. So the other thing that you can do is you can go to calculate, you can choose intersect, and then you can choose your first curve, which would be the blue one. The second curve is a red one. And then for the guess, since I do have 2 points of intersection, you can move your cursor over to the guess, or if you think it looks like it's happening around 2, you can just guess x equals 2, and then at the bottom of the screen, it tells you the intersection. All right, so now that I've analyzed my function, I recreated the drawing right here. The parabola is the lower function, the line is the upper function, and they are intersecting at 0, 1, and 2, 5. So setting up my definite integral, we're going to have the definite integral from 0 to 2. We're looking only at the x coordinates, and then the upper function is 2x plus 1 minus the lower function, x squared plus 1 dx. You can put an extra set of square brackets right here if you want to. And you could go through the process of integrating by hand, but now that we know the magic of Math 9 in the calculator, we're just going to type that in the calculator and you're going to get 4/3. Sometimes you might have a situation where the graphs intersect each other in multiple places. Here's an example of one. The blue curve is called f, and it's a cubic polynomial. You can see the equation of it right there. The red curve is g, and it is a parabola. You can see its equation right there. You can see that they are intersecting each other 3 times, when x is -2, when x is 0, and when x is 2. So if you have this situation, you're going to have to do 2 separate integrals, because this region over here, the blue curve is the upper function, and the red is the lower, and in this region over here, vice versa. So you would set this one up as going from -2 to 0 for the f minus the g, and then for 0 to 2, the g minus the f. Have a go with this problem. All right, so I went ahead and graphed these two functions, or I took a picture of it really, and you can see that over here that we're going to call this region A, the cubic polynomial is above the blue parabola, and then over here in region B, the opposite is true. I should have said this in the other example, the previous example, but to find their points of intersection by hand, you know, if you're stranded somewhere and you don't have your TI-84 calculator with you and you're trying to find the points of intersection, you can just set these two functions equal to each other and solve. I will show you that after I go through the integral piece later. So if you want to skip that part later, then you can. And anyway, we find that the points of intersection here are at x equals -1, x equals 3, and then x equals -3. So I'm going to have to do 2 separate integrals. So first I'm going to do the integral from -3 to -1, where the cubic function is on top, so that's going to be the upper function, x cubed minus 9x minus 9 minus x squared dx. And of course, as always, you can put extra brackets and parentheses here if you prefer. Now that's going to work out to be, well, we'll figure that out in just a minute. Now I'm going to go plus the integral from -1 to +3, where the blue function is the upper function, or the parabola, which is 9 minus x squared, parentheses, minus, parentheses, x cubed minus 9x. These parentheses, of course, especially the ones that follow the subtraction sign, are essential. Do not forget to write those parentheses when you're writing these definite integrals. So when you go to the calculator to get these integrals, or if you do them by hand, you're going to find that this one is equal to 20/3, and then this one is equal to 128/3. So when you add those together, you're going to get 148/3, and that is the area of the regions bounded by these two curves. All right, as promised, I'm going to show you how to find these points of intersection algebraically. If you don't want to watch this, feel free to just end the video. So to find our points of intersection, we're going to set these two functions equal to each other. That's x cubed minus 9x equals 9 minus x squared. This is a polynomial. I'm going to set it all equal to 0. So I'm going to have x cubed plus x squared minus 9x minus 9 equals 0. May not occur to you right away how you can solve this, but you can factor by grouping. So if I group the first two terms and group the second two terms, I'm going to take out their greatest common factor. From the first two terms, the greatest common factor is x squared. So that's x squared times x plus 1. From the second two terms, the greatest common factor is -9. So that's x plus 1. And then, of course, these two factors are identical. So you're going to, essentially what you're doing is you're factoring those out. So that's x plus 1. And then you're left with x squared minus 9 equals 0. So now, according to the zero product property, we can say x plus 1 is equal to 0, or x squared minus 9 is equal to 0. So over here, x equals -1, and here x squared equals +9. So x equals plus or minus 3. And so there you have it. The two graphs intersect each other at -1, at +3, and -3.